Hello, I'm Grayson Evans, KJ7 Uncle Mike. Welcome to another episode of Hollow-State Homebrewing. In this video, we're stepping into the world of glowing filaments, electrons in a vacuum, and engineering ideas that once reshaped the world and might still have something to teach us. We're talking about Thermatrons, or if you prefer the obsolete name, vacuum tubes. This is a tour through the many species of Thermatrons, what they do, how they work, and why you might choose one over another in your own designs. You'll leave not only with a better understanding of the parts themselves, but perhaps with an appreciation of how clever the thinking was behind their engineering. Much of what we'll explore here comes from my book, Hollow-State Design. It's a kind of a field guide to building with Thermatrons, and you can find it on the Hollow-State Design's website, eBay, or through the Electric Radio Magazine bookstore. And yes, the word Thermatron is mine. I coined it because vacuum tube felt totally lacking. Thermatron tries to capture what these devices are. Heat-powered instruments that guide the flow of electrons with remarkable control. You know, it makes you wonder why in 1915, when Bell Labs, the same lab that later invented and named the transistor, and developed the first production triode, they couldn't come up with anything other than vacuum tube? Really? Then think of Thermatron as correcting their lack of imagination. Thermatrons are categorized by the number of functional elements inside the envelope. 3 elements, a triode. 5, a pentode. The names are cleverly literal. I'll walk you through each: diodes, triodes, tetrodes, pentodes, all the way to hexodes, heptodes, and beyond. We'll discover what makes them different and what connects them. Let's begin where it all began. A technology that first appeared in 1907, the diode. A diode has one job: let current pass in one direction only. The idea is simple, but when first introduced, it transformed radio. It made detection reliable, communications intelligible, and slowly it changed expectations about what electronics could do. Inside, there's a heated cathode that emits electrons, and a positively charged plate that receives them. That's all. But in that simplicity is the foundation for everything that followed: the rectifier, the amplifier, the modulator, even the computer. You've got 2 main species: directly heated filament cathodes and indirectly heated cathodes. Both have their quirks and both still earn their bench space in the right design. In the directly heated variety, the filament is the cathode, as you can see in this dual diode rectifier close-up. In the indirectly heated variety, a separate filament heats an oxide-coated cathode. And like semiconductor diodes, they're divided into signal diodes that handle small currents at low voltage, usually with heated cathodes, and rectifier diodes that handle large currents, usually with filament cathodes. Of course, most modern electronics have moved on to silicon diodes. They're smaller, cheaper, no need for a heater supply. Efficient certainly, but a little boring. However, Thermatron diodes do have certain advantages to make them better suited in some circuits. First, there's no turn-on voltage threshold like there is in a silicon diode. Check out the low voltage turn-on characteristics of the 6AL5 compared with a common 1N4148. Semiconductor diodes have a breakdown conduction voltage, typically about 0.7 volts prior to conduction. Thermatron diodes conduct immediately when the plate is positive with respect to the cathode. This makes them a great choice for small signal rectification. However, current flow increases gradually, limited by the internal plate resistance. Thermatrons, like light bulbs, burn out quickly. I hear this all the time. Myth, of course. The typical TV service indirectly heated cathode thermatron should last at least 5,000 hours. The typical incandescent light bulb, it's pushing it at 1,000 hours. Industrial grade versions, typically with type numbers in the 5,500 to 8,900 range, can be expected to last 50,000 hours. That's a long time, with average use of my Collins S-line. Maybe 10 hours a week. I don't expect to change one for as long as I live. Rectifier diodes like this common 5U4, usually used in high voltage power supplies, are designed to handle large currents at high peak inverse voltages, typically 1,500 to 6,500 volts. They have large plate and cathode surface areas to handle the current and dissipate the heat, and they usually have directly heated oxide-coated filament cathodes, since these are more efficient for large currents. Another good example is the hefty 5R4, rated for much higher plate voltages and currents. There are also several advantages to thermatron rectifiers in power supplies. First, since the thermatron takes time to reach operating temperature, the current gradually increases as the cathode heats up. This acts to limit the inrush current to the rest of the electronics, especially filter capacitors, providing a more gentle and safer startup condition. On the other hand, high current diodes exhibit voltage drop in the 10 to 50 volt range due to the plate resistance. Solid-state diodes have a very small voltage drop, but if substituted for thermatron rectifiers, the operating voltage out of the power supply can be raised enough to cause component failure. This is a problem us boat anchor restorers have to deal with. It's sometimes best to resist conversion to solid state. Besides, thermatrons look much cooler, don't you think? Signal diodes like this 6AL5 dual diode always have indirectly heated cathodes. The two diodes and the shield separating them are easily seen, and you can also see how close the plates are to the cathodes. The close spacing ensures only a small plate voltage is required for diode conduction. There weren't that many small signal diodes made. The 6H6 was the earlier two-diode octal version. There were a couple of triple diode versions like the 6BC7 and the 6BJ7, mostly used in color televisions. Thermatrons are hard to get since nobody's making them anymore. Myth, but an interesting story. The supply of thermatrons will never again be what it was in the 50s and 60s. But there are still zillions around simply because of the vast quantity made during that period. The military, in particular, stockpiled huge quantities to make sure spares would always be available. The story of thermatron's persistence is kind of interesting. In the 70s and 80s, thermatrons were mostly given up for dead for most consumer electronics, including amateur radio gear. But in consumer, guitar-oriented pro audio equipment, thermatrons began to make a comeback in the early 1990s. New and old tube manufacturers in Russia and China hopped on the opportunity and began remaking numerous audio-related thermatrons, particularly the early medium-power triodes such as the 2A3, the Western Electric 300B, and classic beam-power tetrodes such as the KT88 and EL34. Now, before we dive into triodes, I want to make a quick detour, a kind of a thermatron origin story. In the early 1920s, AT&T's long-distance telephone lines had a big problem: signal loss. Voices faded into static halfway across the country. Bell Labs, their R&D powerhouse, was desperate for some kind of amplifier. Enter Lee DeForest. He showed up at Bell Labs with a suitcase, a demo circuit, and a 3-element gizmo he called the Audion. Naturally, the engineers were skeptical until they saw it in action. The triode amplified weak electrical signals cleanly and reliably. It worked. That glowing bulb became the backbone of modern electronics, not just in telephony, but in radios, early computers, and eventually television. Bell Labs didn't just use the triode, they perfected it. The first production triode, the 101D, made the first transcontinental telephone call possible in 1915. Improved designs followed: high gain, low noise, ruggedized. The electronic age had officially begun. And get this, a century later, Western Electric still manufactures triodes for high-end audio gear in their new plant in Roseville, Georgia. They're also bringing back U.S. manufacturing facilities to make many more Thermatron versions. Triode is the family name for a 3-electrode thermatron, one with a single grid. The cathode, grid, and plate are analogous to the source, gate, and drain of a FET, with the same polarities and direction of current flow. This is a 6C4, one of the most common miniature triodes. The component parts are easily visible. Try that with an IC, by the way. It's just the Western Electric original 101D, made smaller and more compact. The metal plate is the positive element that collects the electron flow from the cathode. The black coating is used to improve heat radiation. Between the cathode and the plate are the grids. In the 6C4, there is one grid, the control grid. In multi-grid thermatrons, the grid closest to the cathode is the control grid, since it has the most influence on electron flow. The cathode is a sleeve of nickel alloy coated with an electron-rich barium and strontium oxide. It generates an electron cloud when heated by the filament. Inside the cathode is a tungsten filament wire, seen here attached to the socket pins. It's insulated from the cathode with a coating of aluminum oxide ceramic. Other good triode examples are the 6DZ4. It's a medium-gain UHF triode used in receiver front ends. And the famous Western Electric 417A, an engineering masterpiece of low noise and high gain used in satellite communications. By the late 1950s, Thermatron design at Bell Labs had achieved incredible performance. A common variation is the dual triode, a 9-pin miniature with 2 triodes inside, usually sharing a common filament circuit. Before the miniature versions, the octal-based dual triodes, like the classic 6SN7, were a triode workhorse. The 6SN7, by the way, has an interesting history. It appears at the end of the development of the medium-gain indirectly heated triodes. After World War II, the tube got uprated to the 6SN7 GTA, with an increase in maximum plate voltage and plate dissipation. It was used extensively in everything from audio amplifiers to computers. This and many other thermatrons are still being manufactured in China, Russia, and the US due to use in still rocking guitar amps in even 2025. Proof that some classics, like Miles Davis, never go out of style. There were a lot of dual triodes manufactured in the 50s and 60s, including this 5687 and 6DJ8 used in communication receivers. Most have a common pinout and are physically interchangeable. The 12AU7, 12AX7, and 12AT7 are good examples that only differ in their amplification factor. Due to their popularity in high-end audio and guitar amplifiers, dual triodes like the 12AX7 are still being manufactured and have gotten pretty expensive. There is even a 3-triode version, the 6U10, a 12-pin compactron. The compactron, by the way, was invented, trademarked, and commercially introduced by RCA in the early 1960s. This is a transfer characteristics graph, a plate current versus grid voltage graph for the 6C4. Its amplification ability is related to the slope of the curves. The steeper the slope means more amplification, more change in plate current for a given change in the grid voltage. The higher the plate voltage, the higher the slope gets. It's usually desirable to operate in the most linear part of the curve, and in our 6C4 example, this occurs at low grid voltages and at higher plate voltages. The triode works great, but it has two nagging problems: rather low voltage gain and high interelectrode capacitance, especially between the plate and the grid. This limits the gain by the influence of the plate voltage on attracting the cathode emissions. It's always out of phase with the grid signal voltage. In 1919, Walter Schottky of the Schottky diode fame, while at Siemens, had an idea of adding an extra grid between the plate and the control grid to provide isolation. If this new grid is held at a constant positive voltage, it screens the varying plate voltage from affecting the cathode emissions, thus the name screen grid. And the resulting thermatron is called a screen grid tetrode. The other problem the tetrode solves is the reduction of the control grid plate capacitance. As a bonus, the screen grid acts as an electrostatic shield, reducing the control grid plate capacitance. Of course, no free lunch, and the tetrode has its own share of problems. Typical tetrode performance can be seen in this plate voltage versus plate current graph of the 6EV5. Plate current is almost flat above 100 volts and nearly independent of plate voltage, resulting in a greatly increased plate resistance, above 500,000 in some tetrodes. However, below 100 volts, things look a bit weird. The tetrode's dirty little secret. If the plate is operated at or swings below the screen grid voltage, secondary emissions from the plate get attracted to the screen grid, generating screen current. This dip in plate current due to the secondary emission is often referred to as the tetrode dip or the tetrode kink. Obviously, operating in this region would cause tremendous distortion. Due to the tetrode's funky curves, there were very few plain old tetrodes ever made. But the two-grid structure got repurposed as space-charged tetrodes in 12-volt auto radios in the 50s and 60s. With a plate voltage of only 12 volts, it needed something to give the electrons a swift kick. So the role of the control and screen grids was swapped. The grid closest to the cathode, what would normally be the control grid, was operated at a constant 12 volts, and the screen grid was used as the control grid. A couple dozen of these space-charged tetrodes, as they were called, were put in production. In 1926, Gilles Holst and Bernard Tellegen, while working at Philips, came up with the original way to solve the secondary emission problem. They added yet another grid between the plate and the screen grid, making a 5-element thermatron, the pentode. The extra grid's sole job is to suppress secondary emission electrons from reaching the screen grid, thereby eliminating the tetrode kink, and thus the name suppressor grid. It doesn't take much. A few wraps of grid wire works fine. These common 6AU6 well-behaved transfer characteristics and plate curves are typical for pentodes. Solid lines are plate current, dashed lines are screen current for two negative control grid voltages, with the screen grid held at 150 volts. Plate current begins to exceed the screen grid current in the 20 to 30 volt range. The plate current kink is gone. Some pentodes, like the 6BQ5, tie the suppressor grid directly to the cathode inside the envelope. The pentode turns out to be a really hot voltage amplifier, and there were hundreds of different types made. Take the 6EH7. It has a plate resistance of over a megohm and a transconductance of at least 12,500. Because of their high amplification factor and extremely low grid plate capacitance, they're commonly used in communication receiver front ends and IF amplifier stages. Meanwhile, back at RCA, developments were not over for the forlorn tetrode. It's the 1930s. RCA Labs is busy developing new Thermatrons, but Philips owns the patent on the 3-grid pentode, the latest hot thing in Thermatron design. RCA engineers want the performance of a pentode, but they don't want to pay royalties, so they get creative. Instead of adding a 3rd grid, they re-engineer the tetrode by shaping the internal electron flow using a pair of carefully placed beam-forming plates, plus tighter grid alignment. This creates a low-potential space charge region between the anode and screen grids to return secondary emission electrodes back to the anode. Pretty clever. They also align the screen grid and control grid wires so the screen grid lies in the electron shadow of the control grid. This reduces the screen grid current even more, contributing to the tube's greater power conversion efficiency. The result? The beam-powered tetrode is born. A tube with pentode-like performance, high gain, low distortion, but legally distinct. Tubes like the 6L6, the first successful powered tetrode, the 6V6, and the 807 hit the market. They show up in everything from World War II field radios to Fender guitar amps, and they're still prized today for their tone and reliability and glow. It wasn't just clever engineering. It was a workaround that sparked a whole new branch of tube design. Beam-powered tetrodes were used in large numbers in ham radio transmitters, the most common being the RCA 6146. During all this development, improvements were also happening to the design of the grid structures, since grids determine most of the Thermatron's performance. In pentodes and triodes, control is dependent on the spacing between grid wires and their distance from the cathode. Some control grids are constructed in what is called sharp cutoff or remote cutoff, depending on how the control grid reduces the electron flow with increasing negative voltage. In a sharp cutoff pentode, the control grid wires are spaced equidistant. As the grid becomes more negative, the flow of electrons cuts off quickly but uniformly. In the remote cutoff version, the grid spacing in the center is much wider than the spacing at each end. As the grid becomes more negative, the ends pinch off the flow first, the spacing in the center requiring more negative voltage before it pinches off. This will gradually reduce the Thermatron gain with increasing negative bias. While I'm on the subject of grids, I should introduce the frame grid. A substantial improvement in the design of the grid structure was developed by Amperex in early 1958 called the frame grid. The name comes from the mechanically rigid welded frame used to hold the grid structure. This structure allowed the grid wire size to be greatly reduced. To get a feel how small the frame grid wires can be, the photo on the left shows a millimeter scale next to a frame grid, and the photo on the right shows a human hair next to the grid wires. Both photos are from Thomas Mayer's blog. Near the end of the Thermatron era, companies like Amperex were developing Thermatrons with incredible performance. The frame grid allowed Thermatrons like the Amperex 7788 to achieve insane levels of gain with extremely low noise. Equivalent noise resistance of 100 ohms at 50,000 micromoles. Try that with solid state. There are also dozens of pentode-triode combinations in 9-pin miniature envelopes. The 6U8A and 6EA8 are popular examples. The 6U8A was probably used more than any other Thermatron in Collins amateur radio equipment. There are even dual pentode compactrons, like the 12-pin 6BF11, that share a common filament. Not all pentodes use the extra grid as a suppressor. Some specialty dual-control pentodes, like the 6AS6, where the suppressor grid is constructed like a control grid, were designed so that the control and suppressor grids can be used independently for circuits such as gated amplifiers and mixers. I devoted a section in Hollow-State design using the 6AS6 as a mixer in the circuit you see here. If 3 grids are good, 4 or more grids must be better, right? Maybe not. The 6-element hexode, a thermatron with 4 grids, was actually developed in Germany after the 5-grid heptode. It's intended as a mixer, with grid 1 for signal input and grid 3 as the oscillator input, and grids 2 and 4 as screen grids, usually connected internally. It's got no suppressor grid since it was intended as a non-linear mixing device. The only example I can find of a hexode is the 6K8 that combines it with a triode. In a clever design, the hexode and triode share a common cathode and grid 1. The heptode, with 7 elements, often called a pentagrid, with its 5 grids, was developed in both the US and UK around 1933. It's another attempt at making a single thermatron oscillator mixer that mix the local oscillator signal and the received signal in different parts of the same envelope. Within the single electron stream from cathode to anode, the first 2 grids form a local oscillator. Grid 1 acting as the oscillator grid as before, and grid 2 functions as both a screen and the oscillator anode. Grid 3 accepts the incoming signal to be converted. Grid 4 screens this from the anode, and grid 5 is a suppressor grid. There you have it. Examples are the 6SB7 around 1946 and the 6BA7 around 1948. The pentagrid made it possible to eliminate a separate oscillator thermatron, a big deal when Americans started mass producing radios. It became standard in all-American 5 radios when it first appeared in 1934. The octode, with 8 elements, was a further development of the pentode by adding an additional screen grid. In North America, the only octode manufactured was the 7A8, introduced by Sylvania in 1939. It was the product of adding a suppressor grid to the Type 7B8. Hard to believe, but there was a thermatron with yet another grid. The 7-grid no-node, also known as the N-node, also known as what? The only known example of the no-node is the EQ80 and EQ40 from Philips. It was intended for use as a detector and at the same time as an amplitude limiter in FM receivers. The 3 control grids are isolated by 3 separate screen grids. To paraphrase from the Philips datasheet, the principle of operation of this thermatron is unique. In the EQ80, a constant cathode current is modulated by 2 control grids in such a way that the anode current varies in accordance with the difference in phase between the 2 control voltages. There you go. A natural-born mixer if I ever saw one. Fortunately, that's the end of the grids. In practical terms, the use of any of these beyond the pentode is rare. Using a pentagrid for frequency conversion, other than for recreating an old radio design, has been superseded by better, less noisy thermatrons and circuits. Now, I hope you've enjoyed this little tour through the vacuum. In the future video, I'll introduce you to some of my favorite specialty thermatrons, such as beam deflectors, gated beam tubes, voltage regulators, and magic eye thermatrons. In the meantime, keep those filaments lit. Oh wait, I don't want to forget my little shameless commerce plug. Now, there's a lot more thermatrons and thermatron circuit design and homebrewing and Hollow-State design, the 3rd edition, available from my website, eBay, and the Electric Radio Magazine website. If you don't get electric radio, by the way, you're missing out on tons of articles about thermatron gear. You can also email me questions or suggestions as long as they're good ones. 73 from KJ7 Uncle Mike.